Hello, nice to meet you here today. My name is Petr Schwarz. I am from Brno University of Technology from Czech Republic. Sometimes ago I also based company Phonexia that is delivering speech technologies to the market. I was part of the Caldi team, the Caldi development toolkit, and today me and my colleague would like to tell you a little bit about dialogue system, or basically conversational AI, neural conversational AI. So what is the topic about? I will start with short introduction. What is conversational AI? Then I will tell a little bit about neural network language models, transformers, pre-trained models, but I think a lot of this was already here. And then I would like to speak about components that are in these systems, and about end-to-end dialogue systems. So the field is developing or evolving similarly in ASR. So we go more to end-to-end systems. And afternoon, I will tell more what was happening during the last half year, and will give you some practical examples. So what is conversational AI? So you can imagine that you have assistants. You can speak in national language, and you get answer. So it can be a smart speaker. It can be system that helps you over phone. It can be in-car system, home assistants, and so on. So the conversational AI should help you in your national language, basically responds the most naturally to your questions. I would say the field is still far from being solved. So you saw Siri, Google, and so on. Now there is big wave of systems based on large language models, and I would say some of the systems are deployed commercially, but there is still a long way to go. So you can see here you have examples from Google, from Amazon, Apple. There are open source variants. Some of the systems are basically smart speakers, and the processing, the speech recognition, and so on is done on the server. But at the moment it helps you with the basic stuff, like to set alarm, play music, do shopping, and so on. It needs to keep the user context, and the capabilities are limited now. So we have two kind of tasks. The systems can be task-oriented. Basically, for example, you are calling to helpline, and the helpline gives you or try to solve your issue, book air tickets, help to pay invoice, help to resolve technical problem, or there is other option, basically not task-oriented or open domain, and there the goal is to entertain people, for example, during car driving, or to help retired people and so on, kids. So what is the structure of such system? So we can have traditional systems, and there you can find blocks. You can find speech recognition that converts your voice to text. You can often or usually find a block that is language understanding. Understand why you are what you are asking, what you would like to get. Then there is some dialogue management. Basically, the dialogue tracks the states where you are, and it selects the action, what to do, what information to provide, where to ask when to ask to database and so on. And after that, the systems needs to generate some response for you, and this is in textual form. And after that, you need to convert the textual form to speech. This is usually done through speech synthesis. Here is example of a system that we developed for emergency lines, because the emergency lines are overloaded sometimes, and in our country they decided to handle the overloaded calls automatically. So here I would like to show you that it has even a bigger context after or before speech recognition and after speech synthesis. You need to connect it to telephone. So there are some, for example, RTP streams that transfer audio. There is session initialization protocol that where you get the information that the call was initialized or terminated, and in such system you can think also about other modalities, because there can be people calling in different languages, not only in Czech or not only in English, but German and so on. So it may be good to use language identification for repeated calls, voice biometry, and so on. So we are integrated such technologies steps to step. Just for example, how we are here also working with such some data. So for one example of data that can be used, and we will be working with also during the workshop, is multi-voice database. It was collected by Pavel Budziansky from Cambridge, or PolyAI, and if you can see how it is structured. So you have the text. You have the states that you need to identify. So for example, train, and then there are slots that you would like to get, like departure, starting station, end station, time, and so on. Now about your network-based language models. You know this. Basically, you can use neural network to train, that is trained to classify to some classes. The classes can be words. Before you have some features, this can be previous words, and you train the neural network to recognize the classes. If you remove the last layers after bottleneck, you get embeddings that can characterize the word. This was started by Tomáš Mikulov at BUT, then he went through several companies like Microsoft, Google, Meta, JHU, and so on. But what I would like to basically show you, and to be clear, these embeddings are vectors of numbers, and you can see these numbers in some space. So for example, if we look at first 2 dimensions, you can visualize it, and if you have a dialogue, basically the dialogue is some trajectory in this vector space. This is just for remembering or how it is with language modeling. The closed words are clustered closer to each other. So here is example, travel by or go by Škoda, by Tesla. So the car brands are closer to each other. By car, by bus, by train, it will be probably farther, and so on. This is a real example of the clustering. So you heard here about support units. The easiest encoding for neural network is basically one hot encoding that you have a directory of words, and on the index of word you will put 1, and you will put zeros to all other places. But if you want to work with languages like Czech, we have millions of words, and it's not practical to work with vectors that have the dimension of million. So people start using support units, and there are ways how to get the support units. It can be byte pair, that you are starting with characters and merge the most frequent pairs, or you can use word pieces that is using language model in this clustering, or this merging. Now I would like to tell you a little bit about neural networks. So you can create language model with simple feed-forward language model or feed-forward neural network, where you just put at the input context of several words. But after that, people realized that they would like to model longer contexts. So they start working with recurrent neural networks. But after a while, people realized that these recurrent neural networks are not powerful enough. But why? Because when we are doing the back propagation, the gradient is vanishing quickly, basically exponentially. So in practice, it is not working with such long context that we would like to have. So therefore, there was other step, long short-term memories. This is architecture of neural networks, where you have already some context state, and you have gates that can control the data flow. You have input gate, output gate, and you have gate that enable you to forget information, and these gates are basically controlled by some linear layers. So this architecture helps you to go more further in the context, and the gradients can vanish more linearly. After a while, but it is still a recurrent neural network that is looking to pass only. But after a while, people realize that if you turn, for example, the features, you can do the same from future to the history, and it adds some points in accuracy. So after that, BLSTM, bidirectional LSTM, were introduced, where you have layers that go from left to right, and then the next layer goes in the opposite direction, and so on. But why I'm telling you this? I wanted to come to attention, and you can see attention as some continuous progress in the research and development, because there was feed-forward networks, recurrent networks, LSTMs, and neural networks with attentions are even more powerful. So this picture is basically from the listen, attend, and spell speech recognition architecture, and what it does, it helps you to extract information from arbitrary place in the context. So you have some state vector that says what you would like to extract from the context. The context can be a matrix of feature vectors, and then basically you have two networks. One network is converting this feature vector, and the other is converting the first one is converting state vector, and the other is converting feature vector, and the conversion is done in such a way that if the two output vectors, if you do simple dot product, you will get the maximum. So you will get the maximum in the temporal places where you would like to extract the information. After that, you will do softmax over time, and the softmax is there just because of normalization. The information that you want to assign certain weight to the vectors in time. And once you have these weights, you can basically sum the input feature vectors using these weights, and you will get new vector that contains already the extracted information from the input feature matrix that you can process further. Okay, now in the language modeling, or in the dialogue systems, we work with encoder-decoder architecture. So here we can use, for example, recurrent neural networks to encode input features, and then again, for example, recurrent neural networks to decode output sequence. I won't go much into the details because I think it was mentioned here already. Before there were encoder-decoder architectures, but these architectures were not strong enough because there was not the attention. But after that, the attention was introduced to such architectures. So the architecture can focus really on the places, on context that you need. About transformers, transformers are generalization of this attention mechanism. Imagine that you have encoder neural network that encodes you the input to some vectors, and decoder that decodes you the hidden vectors to some output representation. For example, you can have one language at the input and text in one language at the input, and text in the other language at the output. Or you can have dialogue question on input and dialogue answer at the output. So what is interesting, there are several attention blocks. So the encoder can basically extract the information from various places of your feature vectors. This can be representation, encoded representation of input words, but for the answer, you need to know what was already spoken. So there are attentions to the output words. And if you would like to combine the information from input and from output somewhere, and for this there are cross attentions. So now the situation in dialogue modeling is similar as in language modeling for speech recognition, similar with translation. Basically, the most powerful architectures now are based on pre-trained models. The pre-trained models are often transformers, and in case of transformers, transformer is a general architecture, but you can do simplification. You can have the encoder only. This is, for example, something like language model before, or ASR model in speech recognition. You can have decoder only architecture, and you can have encoder decoder. So it depends whether there is one or these two neural networks. And what data it is pre-trained often, very often it is pre-trained on gigabytes of text. I would say the most common data is Common Crawl in these days, and then it is fine-tuned for particular task. Here, just summary of these pre-trained models. So everyone started with BERT. When it went to multilingual case, it was Roberta. After that, based on the popularity of OpenAI, it's GPT. This is decoder-only model trained for next word prediction. Then there is BART, T5, and so on. If you would like to search for pre-trained models, the best place is Hugging Face. Now, this was a general introduction because many of the system components are using such neural networks, and now I will go to dialog systems based on classical componental design, and after that to end-to-end systems. So as I said, one of the first blocks is natural language understanding. The goal is to convert the text to meaning, and we have some dialogue text, and we need to extract information. So for example, information. What is the intent of the user? For example, I would like to book ticket, find restaurant, and so on. Each intent has some slots. So for example, where to go, from, to, what time, what is the traffic. If it is car, if it is train, and so on. And there are some tasks that can help to this. This is like name entity recognition, because many of the slots are entities, and then if it is more natural speech, you can do some coreference resolution. For example, that it means a restaurant, and so on. What are the natural language understanding challenges? Basically, speech, especially spoken, is not grammatic. You are not producing grammatic sentences. There are disfluencies. So, for example, in speech, you have fillers, repetition, pauses. You have some fragments. One of the difficult part is self-repair, because you start the sentence, and after 2 words, you realize that you wanted to tell something else, and you will repair yourself. Then we need to deal with ASR errors, and there can be 2 kind of errors. There can be errors from statistics. There can be errors that, for example, the ASR and your NLU unit has different dictionary, is trained on different data, and basically the components do not match. Some things can be taught in 2 different ways, and there are also out-of-domain utterances. So now, how this can be done? In many systems, it is done easily. It is done by keywords, regular expressions. So I would say this is even still the case of many commercial deployed systems. The commercial systems are usually very simple. If we speak about intent classification, it can be, for example, sentence embedding based on neural networks plus simple classifier, for example, logistic regression. This is also how it is done, for example, in our system with emergency lines. Slot value detection, there are also different possibilities. You can do the binary classification if it is, if slot, for example, time is presented, you can label the data with some beginning of slot, end of slot, inside slot text. And in many practical systems, you are doing also the lexication. Basically, if you detect that you have slot, you either you will extract the information, you will use it for your query to database, but you are working with some tags further. Here is one more modern techniques you can use. For example, BERT for NLU, and here in this work it was used for combined slot and intent detection. Often you have special start tag. You will use the BERT. You will add a linear layer, and usually softmax on the top of the BERT, and you fine tune the BERT for different NLU tasks. More powerful techniques are basically models that are pre-trained for dialogues. So for example, here we have architecture with two transformers, and the transformers are trained for response selection. So imagine that you have dialogue, and you have, for example, question and answer, and you can try to classify if the answer is response for the question. And in such case, using such case, you can you can create a pre-trained model that is more powerful than the initial BERT. And after that, you can again fine-tune it, for example, for slot tagging, intent detection, and so on. Okay, I will skip this. Now about the other component, I said there is speech recognition, there is national language understanding, and then there is some dialogue manager. The dialogue manager should decide what is the next state, the action. It has dialogue history, it tracks the dialogue states, and it uses some policy, what to do, how to provide you information, where to query a database, and so on. So the dialogue state, you can have like fixed dialogue states, for example, price, cheap, food, Chinese area, for example, close to river, or you can have probabilistic dialogue states. The probabilistic dialogue states or slot values are more powerful because during the dialogue, you can still ask, did I understand this correctly? Did you mention this, or are you wanted to go to this? Do you want to go to this city? So it can be hard crafted, or it can be probabilistic. And with the dialogue states, how it can be basically approach. We can have dialog state that is conditioned on the previous states. This approach is common in the deployed system, or you can have basically natural language understanding over the whole dialogue, and you have some dialogue understanding over the whole data. So basically the question can be, is this slot present, and so on. So I would say the option B is like generalization of the old graph-based architecture. Now about action selection, so deciding what is next. So we need to basically control the coherence of dialogue. So if we are not sure about extracted information, we need to confirm. For example, do you want to go to Chinese restaurant? The actions are linguistics, that some information is provided to you, and non-linguistics. So such systems need access to your backend. So here are some possible actions, basically that I mentioned. And now about the dialogue, how it can be represented. I would say the most of commercial system is using some finite state machines that you really every question and answer is encoded. Before it was encoded through keywords. Now there is the train intent detection. There was one possibility to encode it through frames. Basically, there is standard voice XML that goes in this direction, or the simplest possibility when you want to have a quick dialogue system is rule-based systems where you encode it in code, for example Python, and the advanced systems are statistical. The statistical systems are often trained using reinforcement learning. Why reinforcement learning? The easiest way would be if we have trained data to use supervised training, but the supervised training is not efficient with multiple good answers. We want to provide negative feedback, so reinforcement learning is able to handle delayed feedback. We probably want to give some delayed reward, not for the actual state, but for the whole task. So, for example, the information that you were looking was provided, and so on. And there is a very interesting area or domain. Basically, what to do with access to external systems. The access is done through API, how to get information from databases, because it's not easy to derive your gradients or get your gradients through API calls. So this is just quick note. What is reinforcement learning? you have agent and the agents is doing some actions and you have environment and you are getting some feedback. You can have feedback for some immediate actions, but you would like to maximize the feedback over the whole dialogue or set of dialogues. So what are rewards in such systems? It can be hard crafted. For example, one case is that you give -1 for each basically dialogue turn because you want to prefer short dialogues in contact centers. If it is for entertainment, if you can give possible feedback, if the dialogue is successful, again, for example, when you are asking for information, you give high reward. If it is unsuccessful, you give big negative reward. What are the difficulties? The domain knowledge is needed, and it is hard to do it with people, so you need to search for ways how to do it automatically, for example, how to simulate users and so on. Now, one of the latest or the blocks, when you decide what you will do, for example, if it is sharing of the information with user, you need to generate the answer. Again, in the systems that are deployed now, it is done through some templates. You have answer and you had some text where the information will be included, the information that is retrieved from a database. This is preferred by the managers from contact centers because it is deterministic and they don't hesitate to deploy it. But it is not fluent for users and some, for example, generation through language models or multiple templates and so on can help to have more natural dialogues. Okay, so this was about the blocks. I was not speaking about synthesis ASR because for ASR there is other team on this workshop, and now I will just compare the end-to-end systems and the component systems. So in end-to-end systems, the dialogue systems is usually one or several neural networks that is trained together. What is the difficulty with component systems? I would say that the component systems are easier to maintain, are more predictable, but if we speak about errors, the ASR can do some kind of errors, the NRU does different kinds of errors and so on, and the errors accumulate. If you have end-to-end system, you can optimize everything together and you can have more natural dialogues. But on the other side, if you have such systems, it is easier to screw the whole task. Yes, this is what I said. In case of the end-to-end systems, I said it's easier to screw the task, but there are drawbacks of current approaches because, for example, the large language models, again, it needs a lot of training data, a lot of annotation, and still the systems have hallucination and so on. And the managers are really worried about deploying systems where the answer is non-deterministic. So we can get systems that can have better customer satisfaction or get better you can have better feeling from using them, but in some cases it can provide really strange answer. Maybe it is close to human behavior because even if you call and speak with people, sometimes you are transferred to other people because they don't know, but the same situation is here. Example of such system, there are several systems based, for example, on GPT-2. Such systems, for example, Solist is one of them. The system is separated to 3 steps. In the first step, the system is used to get the belief state, get the slot values. After that, there is a query to database. The database is usually external, and after that, the model is called again to generate prompt. What is nice in this system that the same model is used for both state, getting the dialog state and generate the answer. Here is the way how is it encoded to the neural network. It is GPT, so we have one sequence and everything is encoded through text. So you will get the text like the output is slot tag, state tag, slot tag, and so on. What is the time?
9:50.
Okay. So now actually we created a team with people from Charles University. So I will tell a little bit about their work. If we speak about this Solist, you can download the code, you can play with it. It is trained for multivoice. The multivoice data are available, so it's easy to start. The Charles University already continued with the work, and they did several improvements. Here maybe what is interesting, the training, that it is state prediction, but there is also other auxiliary task that is consistency. So you have basically question and answer, and to make the task harder, you will try to classify if the answer is the right answer based on some corpus, and this improve the accuracy. So this is then there was work done on basically cleaning the data and why is it here? Yeah. There is data augmentation. So what is interesting on this work? In this dialog system, is really hard to get training data, and you know that people are able to get or to represent some knowledge through or some request or share the knowledge through different words, different phrases. So in this work, they basically use speech translation system, and they converted the original data to many languages, and they translated back to English, and through this it was possible to improve the results. So this is interesting approach how to get a better system. There was data cleaning. There was unlikelihood loss because if you share some information, if you are using the same sentence every time, it is not natural. Basically, you have feeling that you are talking or chatting with a robot, but the same words were penalized, and this behavior was attenuated. And there was also some sampling for output diversity. Okay. Maybe now I would ask about questions that you have for this introduction about dialogue systems. I was not sure what exactly was presented for these large language models, so I tried to make it faster, but I expected that you will have questions, and then you can have questions about, for example, the Charles University systems. We have guys from Charles University here, so please let's ask questions.
Thanks, Petr. I'd like to ask, you showed, I don't know, the slide number, there was the transformers for dialogues, and there are two transformers in parallel. So I'd like to understand why is that? Yeah, this one.
Okay, because the goal is to get better embeddings. So you want to represent the text by embeddings, and you would like to go closer to the dialogue task. So one possibility is to use the transformer to encode the question and to encode the answer, but then you would like to fine-tune the transformer somehow. And in this case, if you can see here, you have one branch for the question, one branch for the answer. I think the parameters are shared, but there is a similarity score, for example, dot product, and now if you have a set of questions and answers, but you can create trials that have answers that are really answers for the question, but you can sample the answers or responses from your database. And in such case, you will create a classification task that and you have objective function that you can optimize and get better embeddings. Still, you need to do fine-tuning for a particular task, for example, slot tagging, interclassification, but the embeddings are better.
So the pair with the highest similarity score will be selected as the answer to the question?
Actually, yes. If you have two pairs, you have questions and response on question and answer. And when you are creating the data set, you have basically correct question and answer, but you can have answers to the other questions from the corpora, and you can basically have pairs that where this two match and where this doesn't match, and the task is to really distinguish what is the case.
So if you can jump to the slides with the architecture of the end-to-end model, the GPT-2, actually, that's the one I'm interested in, because we did the similar experiment, but there is one thing that we never...
Do you know which
yeah, further, I will tell you. Yeah, the GPT-2.
Oh, okay, so I prepared the detailed explanation of GPT-2 for.
No, I mean about embedding. Yeah, here that was there, or maybe a little bit further. This one. This is exactly what I wanted to ask about. So the idea here is that you have one model that basically where you insert the database queries, and you have the answers. I was trying to do an experiment to just fine-tune a GPT model on a dialogue, and the thing that I realized is really, really bad. If you have a task-oriented dialogue, there are questions where basically the model cannot learn the answer, because the same question can have multiple answers. So the model is just guessing, and basically you are trying to train something that is impossible. Once you insert the query, the response of the database inside the same string, you basically give the model the opportunity to actually train on a real data. But that training process basically requires for the model to not predict these. Is it possible to do that in GPT fine-tuning? For the error to not try to predict these parts during the training?
I'm trying to understand.
So if you imagine the DB state that you have over there, so that is the thing that in the runtime, you have it from database. So you do not want the model to teach itself to predict these, because you know that those have to be given. You will not be able to predict them because that's something that comes from backend. Maybe Ondřej is waving on me, whether maybe you can answer that one.
So basically, there is very often the step of delexification, that the slots are replaced by some text. For example, this is name. Not sure if the GPT was trained in such way. I think it is possible, but it is done for the generation part. Actually, yeah, maybe if you have a detailed.
Thanks. So you are exactly right that if you have like one context, you can have multiple answers. But if you know the database results, actually, that you can generate freely because you are very much conditions. So actually, Vojta Hudeček did quite nice trick that he tried to predict directly the API calls So you have like the context, you predict the API calls, but this was one task, predicting API calls, but he got the reply, and he did multitask training with second task, where on the input you have the results, and you generate the answers.
Right.
So you basically ignore the problem, and you just use the multitask training. It has the same vocabulary, maybe a little bit different on the API call part, like the inputs and the arguments, and the results formatting, but all the other vocabulary is the same.
Okay, that is exactly what I wanted to hear. And the second part I would ask about is, have you actually observed the reduction in hallucination? Because that would be my guess. If you fix the task properly, then you have the right context. So did the hallucination actually decrease?
I'm not sure about hallucination, but what I observed is, like it's not particular on this experiment, so I cannot comment on that. But what I observed is catastrophic forgetting, because if you have multiple answers and you like shuffle them, not like you don't see them exactly in the same order. So, for example, you have 3 answers, A and B and C, and you first see the A, then the model learned to predict the B and then the C. So it already very often forget the A in the meantime, and sometimes it even tries to rotate, like always forgetting the one of the answers.
That is actually super interesting. Thank you.
So okay, it would be nice to see what is the predicted query to backend, if it is SQL command and so on. But it's also a nice task. So maybe are there any other questions?
So this architecture, I had a bunch of questions about that, and maybe if I ask too many questions, you can defer it to a later discussion. So the first thing is, when you decode the belief state, right, it needs to be something which can then go into your backend and generate a response. So the first question was, how do you make sure that the decoded belief state is legal? And I'm assuming you'll put some constraints on the decoder. But then what comes back from the DB is some kind of structured information. Mm-hmm. So the question I have is, what are the challenges in converting that into something that a ChatGPT can consume? Because ChatGPT just works on text. And if you got like a table with numbers, what will you do with it? Where will you add the database semantics into it, and so on and so forth? That's one question. Because it's one thing to talk about train time tables because there are city names, but imagine if I wanted some information about the weather. There are going to be numbers from the meteorological database and the units and so on. That's one. So to me, that yellow part is not obvious. And then the other part that's not obvious to me is in the blue part that you generate, right? So there is some part which comes directly from the yellow bits. And then there is some part that is real generation, which is the real response. The response is going to ask a question or going to clarify something or something or the other. And those are two different things to learn. One is to learn what information from the DB to provide the user, and the other one is what to say about it. Like, there are 12 trains from Boston, or do you want, it's not clear to me at all how the system will distinguish the two things. And if your objective is something simple like cross entropy, which weighs both of them equally, I'm not sure how easy or hard it is to learn. So what are the issues both in how to present the yellow bit and how to separate the two different things that are in the blue output?
I think I don't have the pictures here, but so usually you are providing the belief state. You are providing the DB results. It is very often it is text saying slot name is this text. For example, this departure time and so on. So I think with simple answers, if you, for example, select the first row from the table, it's quite doable. I think the question is what to do if you have really many answers in the database, and I think there is still some heuristic. Probably it may be presented differently to the response generation. If you have one answer, for example, the train is this, and it can be presented differently if you have, for example, three possibilities, and one way is to really reduce the number of possibilities in the backend, that it is not returning then trains, but it is reduced, for example, to three options, and anyway, it is hard to share the information, for example, through voice, through telephone, and I think the dialogue needs to be more structured. For example, there needs to be other questions. Are there more trains, or is there something that goes later, earlier? Not sure if it is answer to your question.
No, it is a partial answer. You said that you will insert these texts which do the database semantics. It will say, like, start departure time this, arrival time equal that. But then the question becomes, the departure time is going to be a number. Now, is that local time at the destination, local time at the origin? Is it a 24-hour form? Basically, there are all these things, right? Like, imagine weather information. If it says temperature 72, is that Fahrenheit or Celsius or Kelvin? What exactly are we dealing with? So it's not clear to me how the database semantics get into the yellow bit. And those, it looks like it'll still need to be handcrafted.
Yeah.
It's not. And secondly, once you do that, on the output side, how do you then make sure that you're remembering to use the units in the yellow part and not making a hallucination? This is a hallucination. It might say, oh, the temperature is going to be 78 degrees Celsius tomorrow. I mean, yeah, right. So
what is the important information? If we work with end-to-end dialog systems, it doesn't need less training data. So it is still it needs heavy amount of data, and the systems are trained for particular customers. So for example, if it is for Czech Republic, there is one time zone, so it removes this how to set inconsistencies. But if you would like to have general system, for sure, there needs to be other inputs, and if we want to move the it needs to be either handcrafted, but if we need or we would like to move this to the model, I think there would need to be other slots that are like contextual slots that says the time zone is this, and so on. Not sure if it would help to get less hallucination, because I think we are still not there. The most of commercial deployed systems are component based, and they are far from such end-to-end systems.
Ask others to ask questions, but let me just make one comment. Long ago, when people were working on ATIS and other dialogue systems, some IBM guys actually did this. They treated the conversion from the user input to the database query as a SQL, like English to SQL translation problem. They actually built a translation model for it. So you just produce an SQL query and then do something with its response. So there was Kishore Papineni and some others. So yeah, okay. More questions?
So I think that there are we are close to this situation, but I think it's a more conceptual way how to do it. But I think in this case there will be many corner issues. What if the query is not valid? What if the tables is empty and so on? So maybe solving these corner issues will be much harder than to have handcrafted system. Okay.
Thank you. I just have one question about the specialty of the conversational model compared to the general generative model. So when we talk about the generative model, when we have a text to complete or generate a text or a speech or image or whatever is it, the modality, we have an objective over there, but here, what is the speciality of the objective function that we have in conversational AI? So we don't want to just answer a correct, just to answer correctly, but we want to keep the conversation going on or answer the question as soon as possible. So there is some term that I'm trying to avoid it, but it's the engagement of the agent. What's the role of this aspect?
So I would say that compared to, for example, just predictive language modeling, here we can have many objectives because if the system is trained for contact centers, it is one objective is, for example, to have the shortest calls because every minute costs something to the company. It is there is very often customer satisfaction rate. If it is selling contact center, it is how many items were sold. There are systems for engagement in car or for people. These are developed, for example, by Czech Technical University, and because they won the Alexa prize several times, and there the main objective is to maximize the time that is spent with the device, with the system, because if people are with Amazon Echo or such devices for a longer time, there is a higher chance that Amazon can include some advertisement or sell some products. So really, there are many objectives.
Is there any technical aspect that we can implement such a fit? Because all that you mentioned was, I can imagine, is post-processing for evaluation of the system. But can we integrate such an objective in our loss function or our training as well?
It can be done on several levels because we have some pre-trained model that is for test generation. Then we can have a pre-trained model for response generation, for state tracking, and so on. And I think that such criteria can be included in each of this stage.
Thank you.
I'm thinking how to explain it better, or to come with some examples. Don't have it in mind now. Actually, if it is about this entertainment, the time is quite easy objective function. Okay, any other question? Okay, so then I think we can have a coffee, and thank you for attention. Okay, so welcome to the next part of my talk. When we were discussing what to present afternoon, we were maybe when we were preparing our topic for workshop, we were thinking about some approaches, but what happened during last few months in the field of large language modeling was fantastic, and we said we need to react to this during our workshop work, and we said we need to share a little bit this knowledge. So my follow-up talk is about large language modelings. There are things that relates to our workshop topic, so it will be focused on dialogues, and I think it will arise also a lot of questions. You heard about ChatGPT. Many of you are using it every day. So I will start a little bit about GTP. Then I will tell about Instruct GPT or instruction training. I will give you some timeline or overview what was happening during past few months, show you Hugging Face leaderboard, and then we start or we will discuss some techniques, what makes the research or your experimenting with such models possible. And colleagues prepared some tasks where you should be able to work with such big models yourself. And there is one more session about evaluation of such language models. So what is GPT? GPT is a transformer that is trained for prediction of next word. So imagine that you have some word context. So for example, I am, and you would like to predict next word. This is, for example, I am here, I am at home, and so on. So you would like to get some probabilities. What is the next word I want to pronounce? And the GPT, it is using, they say, or we claim that it is transformer architecture, but the architecture is very, very simplified. There is a decoder only, so there is not the encoder part. So there is decoder, there is the attention mechanism, and then some classification layers. What is the training criteria here? There are several NLP tasks. Some of the tasks are classification. For example, you want to classify sentiment, if it is possible, positive, negative. There is for example, similarity, how two sentences are similar. There are multiple choice options like query answering. So you give some context or query, you give answer, and then you can recognize what answer is correct. Yes, so there is entitlement. So you have some promise or text. You have hypothesis what can be conducted from the text, and you should classify if the result supports this or not support, or if it is neutral. So here are equations how it can be written. We have some corpus of tokens. So we have sentences. Then for the first layer, we do some encoding where this is our embedding matrix. Here is U is the context of word. So we convert the words to some vectors through this embedding matrix, and we add positional encoding that is UG. And after that, we have this transformer decoder blocks. This is basically what is on the left side. So here is the encoding, self-attention, skip connections to propagate the gradient better. There is layer normalization, feed-forward network, and again layer normalization, and then the classification tasks that are used for training. Usually there is some softmax. So the language modeling objective is this. We want to maximize log conditional probability of the predicted word, and for supervised training, I said there is usually a linear layer, softmax, and again the objective is log probability of the class. And what was seen that if we do the fine tuning for particular class, it helps if the task specific objective and this language modeling objective are used together, so that there is some interpolation of these objective functions. What is the difference between GPT-1, GPT-2, GPT-3? There are GPT other models. So it is mainly about the data it is trained for or on, and it is about the model size. So GPT-1 is 120 million parameters. GPT-2 is 1.5 billion parameters. GPT-3 is 175 billions, and new models are even bigger. Now, what is instruction training? I would say this is what makes these large language models so popular, usable for practical cases. This is why ChatGPT got such publicity. The instruction training started with collection of data. There were people asked to get or create questions and also prepared the answer, prepare the wanted answer. So for example, if you ask what is the most popular event here, so someone prepared Le Mans and information about the car races and prepared it in such form that the guy wanted to see it in this form later. So in such a way, there was a database created using some crowdsourcing. I think open AI were using people from Africa because the cost was the lowest there, and this helped to train or fine-tune the model for answering this question, or basically doing simple tasks. So the task doesn't need to be only to answer question, but it can be create list of most popular, I don't know, football players or soccer players, all possible tasks. But when you train the first model in such a way, you will get a model that when you use this model for text generation, you will get a lot of hallucination. People will like some answers, but they will dislike many answers. So therefore, OpenAI used the crowd again, and they took corpora with these questions and answers, generate several answers, and asked the people, please, can you rank the answers, put the one that you like the most on top, and the worst on the bottom. And what they did, they trained revert model on this data. And in the third phase, they basically use this revert model in the let's say dialogue policy to preselect the right answer that is presented to users. So the system generates several answers, but only the answers that the systems consider to be good enough for presentation to users are presented. Now, how OpenAI got the set of questions and answer. The first approach was that they were asked to create some arbitrary tasks that have enough diversity themselves. Then there was a few shot approach, basically they came with instruction and they were asked to create multiple queries and response for this task, and then there is OpenAI API, and people are asking every day, please can you add this task? I would like GPT or ChatGPT to be smarter. I would like other tasks. So again, the most popular tasks goes to annotators, and they are preparing the sets of training pairs. Here, I am sure most of you saw this page. I just asked the question very slamans, and I got quite a reasonable answer. Why I am showing this slide? I wanted you to see this and to see this. One of the main reason why OpenAI released the page publicly was because they want to collect the feedback, and when you are using the systems, you are providing the feedback through these buttons, and this is used to retrain the whole systems time to time. I would say that ChatGPT and OpenAI open box, they basically it helped to make these are very popular, and actually it happened around the time when we had the workshop preparing meeting in Baltimore, and in that time we were discussing our topics, and this was not in mind, but what happened after that was fantastic. So we said we can't ignore it. So it was in November, and since that time I think all the school kids are using ChatGPT to help them with essays. Basically, all of their presentation, it is in Bing. Basically, Microsoft incorporated it to search engine. Google had to react, so there is Google Bard. Unfortunately, it is not running in Europe because of the regulations and so on, but it is running in many countries. But what is the message, or also what is fantastic, the training cost of this was huge. If you read about trainings costs for these large models, it is usually in millions US dollars. So it is not easy to do basic research on this, but I will show you how this changed and what techniques can be applied that everyone can be working with such models, and Ondra Plátek and Santosh will show you afternoon how to really do some research work with such models practically. Here I wanted to show that this is not happening just in our field, in NLP, in speech processing, but these large models are cross-domain things. Here is other product from OpenAI, OpenAI DALL-E, and what we can do, we can ask textual queries, or we can provide textual description, and that is here. A bubble of soup that is a portal to another dimension. This is example from OpenAI blog, and there is an encoder that encodes this text to some embedding. Then there is a neural network called Prior that converts the textual embeddings to visual embeddings, and then there is a decoder called Glide that generates such nice pictures. So a few months ago, when I wanted to prepare a presentation, I was searching internet for hours. Now you can give description, and you will get the pictures or the images very quickly, and it saves you a lot of time. So now, actually, you can access ChatGPT or other their models through API. If you speak about speech recognition, there is Whisper that you can download. You can play with it. You can fine tune it. But and actually GPT-2, this model that is not fine-tuned for instruction, you can use it, and people are using it as a starting point for dialogue model training. But what really opened these models for research was a step that was done by Meta, and Meta released Lambda model in February this year. The model has several variants, starting with 7 billion parameters and ending with 65 billion of parameters. The code to run these models for fine-tuning and for inference is available. And actually, what I think, even such big models are, it became practical even for some applications. So I think we will see this 7 or 13 million models in our laptops or in our companies very soon. These models is available for non-commercial purposes. Researchers can work with it. But what happened then? I like this article that was published on this server. They claim it is leaked Google communication, but I think it is a very nice overview of these large language models and steps that happened, including links. So I recommend to look at it, and I will present a few steps from this. So here is what happened next. So in a while, we saw implementation of these large language models from Raspberry Pi. If you don't know what is Raspberry Pi, it's a small computer, cheap. You can have it in your home automatization. So it worked. After that, I think Stanford released Alpaca. that is already instruct fine-tuned lambda, so it is closer to ChatGPT. But what is interesting, it is possible to be trained on a single NVIDIA card, this RTX 490, so it is even not a professional graphical card, it's a game card. And why it is possible, it is because of LoRa techniques, it is low-rank adaptation. I will tell a little bit about in a while, and Ondra will help you to use this technique during our practical exercise. Then there was work done on quantization, so it was still hard to fit such models to graphic cards or to our computers. So there is for bit quantization. We will use this during our exercise too. After that, there was Vicuna model introduced. What I see, what is interesting around this model, that there is a ShareGPT web page where people upload conversation from ChatGPT, and these conversations were made or are publicly available to other researchers to train their models. So basically, the work or the annotations and the investment is slightly moving also from OpenAI to research community. Not sure if they will OpenAI will like it, and how for how long the web page will be on. But it is happening. It helped in training of such model. So after that, GPT-4 was released. This is actually nice because you can download installer, and you can download many of these models for your computer, and if you are working on offline, you can have your own ChatGPT style assistant on your laptop. Many companies are not allowing people to use ChatGPT from their networks, so there are possibilities, and I am sure that we will see many company assistants soon. So after that, there is a new model, Cerebras. I saw the association that it is seen as GPT alternative. Here, it was trained from scratch, I think, on open source data or free data, and it means that after that the community is not more longer dependent on Llama only. So there are more models, and there are some tricks that enable the training. So it is interesting to read the article, because the tricks how to make these models practical, how we can train them, are there. So, and after that, we saw already works that enable to train or to fine-tune such model in, for example, 1 hour. So it's making it practical for experimenting. Some of the techniques will be presented in a while. Okay, and just to finish it, in April there is Koala. It is trained entirely on free data. They claim the cost is $100. There is community effort, Open Assistant, that is already using reinforcement learning from human feedback. If you remember the slides within the instruction training, the last part was basically include some reinforcements learning part. The same is done here by community.
And this cost of $100 is to train from scratch or to fine tune?
So not sure if exactly. I think here it's fine tuning. So. But if you go through the article, there are really costs, and you can see what was the amount of data, time, number of graphical cards, and so on. Okay, so this was the timeline was still April, but what I see that the models are appearing every day. So if you want to do your research, it is good to just follow up the progress, and if you want to see what's the actual model, what to look at, I advise you to go to this Hugging Face page. It's Hugging Face leaderboard, where you have several models. I would say that there are hundreds of models in these days, and you have several tasks that are used for evaluation, and the tasks are described here, and you can select a model that fits your task the best. So based on the evaluation set, based on the model size that you would like to deliver, then based on the inference times and so on. Okay, now I will go through some of the optimization techniques that made the use of these large language models by you possible. So one of these techniques is LoRa low-rank adaptation of language models. So why we are using it? It enables us to fine-tune the large language model with reasonable cost. So it makes it practical for many downstream tasks. So it reduced the memory consumption. There is no additional latency delay or latency during the interference, and in the original paper they tested with GPT-3, Roberta, Deberta, GPT-2. Actually, I think it was introduced by people from Microsoft, and the code is available. So it is one possibility to use in your research. How it works? Imagine that we have our transformers. In the transformers, there are some weight matrices, and what we can do, we can factorize this weight matrices to 2. And the multiplication of these matrices has basically this matrices has much less parameters than the original matrix. If it is used for adaptation, the original weights are still there, but we have these 2 matrices with learnable parameters stored in parallel. What is nice that if you want to do the interference, we can either use it in parallel and have separate parameters for many downstream tasks, or we can evaluate or enumerate it explicitly and add it to the original matrix, and then you have no additional inference costs. So it is basically here. Here are the original weights. These are the part for adaptation, and you can see this is a multiplication of matrix B, A, and X is your input. It can be applied to selected matrices in our architecture, and based on this direction, and based on the matrices that they are adapted, you have the number of parameters that can go really from the low number till basically all parameters that are in our transformer. I don't know if I have the initialization. The A matrix is initialized to random Gaussian noise, and the B matrix is initialized to 0, and then you can train it using classical gradient descent. Now we have nice adaptation technique, but we may want to reduce the memory consumption even more. So for this, I'm sure you heard about quantization. It can be applied here too. So there is article Quantized LoRa that is doing this, and the weights are stored at 4 bits. What is interesting, it is quantized for the storing of the parameters only. When the parameters are used, these parameters are converted from 4 bits to floats, then uploaded to CUDA cores, and after that they are again quantized to 4 bits. There is no hardware for direct processing at the moment, so the inference is relatively slow, but you know that you have often difficulty to load the models to GPU card memory, because many of the cards are older, and the process of buying new cards for your university's companies is usually delayed. So maybe other tricks that are there, they use double quantization to reduce the storage space even more, because even the storing of the quantization constants costs something. It would be about 0.5 bits per parameter, so they were using double quantization to go even farther. and there are some optimizations in the implementation. So for example, if there is not enough memory at the GPU, the data is moved to the main memory and so on. Now, this is about other techniques that is used in for optimization of these large language models, and we were speaking about attentions. So people are using flash attentions instead of attentions for training. Why? Actually, here I just copied the equation from a transformer. I'm sure you all saw these equations. So there are some queries, keys, some normalization values. There are matrix multiplications, and there is this softmax function. Then there is input sequence where you have the sequence is n, and then you have some dimensionality of your embedding space. So this is the size of the feature vector, but what is even more important, if you go through the math, you can see that if you go through these two matrices, it's here. We need the dimension length square storing space. This is a reason why when we are using transformers, the sequence lengths are always or very often limited. It is segmented to smaller chunks, and so we would need to do it for here to store the matrices, but it is true also for this softmax, and computation of softmax is quite costly function. So how it is solved? In GPU, we have this memory architecture. There is a memory that is associated with each CUDA core. Then there is memory on the GPU card, and then there is a memory that is in the computer. And what we need, the best is if the whole computation is here in this part of memory. We would like to compute the softmax without accessing the whole input, and we don't want to store some intermediate results, we would like to do it as efficiently as possible. And there are two approaches. One is tiling that splits the computation in the block, and it sends it to GPU card in blocks and accumulates some statistics. And then there is the computation that optimize where the statistics are stored and how there is some sharing between forward pass and backward pass. And they claim that the speed up is like 7.6 times for GPT-2. Other techniques is maybe back to this, you can ask how how you can use these techniques. These techniques, in these days, many of these techniques are called experimental, but they are used to train these big models already, and these techniques are implemented in PyTorch, Versec, and so on. So if you want to work with such big models, go to these toolkits and look for these techniques, and you can usually enable it or disable it, and it's good to know what is behind, because then you won't be surprised what are the results. So the other techniques that is used in these days is fully shared data parallel. This is actually parallel training algorithm. Before, the common practice was that the model parameters were distributed among several GPUs, and all the GPU had the whole copy of the model. But if we are training a large model, so we often are not able to fit the model even to one GPU. So that therefore there are new parallelization techniques that can separate the model to smaller chunks and send the chunks to particular GPU, and then to compose it back. And there is also option that if there is not enough memory on the graphical card, you can or it is possible to offload the memory to the main CPU memory. So of course this is a technique that enables us to work with the memory more efficiently, but on the other side there may be increased cost because of communication, and again this is for example in PyTorch. The other model parameterization techniques is model parallelism. It's tensor parallel. I think if you implemented some models and did some optimization, you were using this already. So if you have some function and there is multiplication of matrix X and Y, you can separate it to two blocks. Here Y to two matrices, and X like this, and you can basically then to do it like this, and compute one multiplication on one GPU card, and the other multiplication on other GPU card, and then compose it back. So again, you can look for it in your toolkit, and it can help you to work with models if you don't have enough memory. Okay, so now we had the overview of optimization techniques. Maybe I will mention one more optimization technique that was used also for one of the models in the timeline. People are using reparametrization trick that they are able to train smaller model, and then at some phase of training to upscale the model and fine-tune it or do the second part of training with larger model. So I don't have details here, but and I saw it firstly when I was reading about this optimization technique. So it may be also something to look at. So it is not easy, but someone already used it. So it's possible to repeat the work. Now about the exercise. The first exercise was prepared by Ondra Plátek, and we will take GPT-2 or Llama recorder only model. In our case, it will be simplified, and we won't use any API call. We will train it for next word prediction. Basically, you will get simple dialogue model. There will be instruction tuning. The data sets that we will use is multi-voice. This is the task-oriented dialogue or corpus. There are several tasks, and we will use quantized LoRa for the fine-tuning, and actually by switching the parameters or options, you can compare the training using this LoRa and training from scratch. Now I will switch or go further to our workshop topic. Basically, our team at workshop is composed from people from universities and industry. And when I was working around companies, the usual feedback was we spent a lot of time on data scientists because they code our dialogues, and it is really costly, and we would like to do some data structure or dialogue structure discovery automatically, because many times when the people come to customer, even the customer doesn't know what is in the data. So we said, okay, let's meet and let's try to approach this task together. So the initial idea was to do it through some clustering of embeddings, but in these days we can't just oversee or not to see the large language models, so maybe we will use also other approaches. So here I will tell you a little bit about approaches that we tested already, and one of these approaches will be on our exercise. It is prepared by Santosh, and it is using k-mean clustering of semantic embedding, and the other possibility uses variational recurrent neural networks, and it was tested by Vojta Hudeček from Charles University. So about the clustering of embeddings, we will use multi-voice data set again. We focused on restaurant dialogues only because we wanted to have something that we can play with quickly and what can be visualized. The dialogues have 14 interactions between the system and user, very often 7 questions and answers. We will use LAPSI embedding. These are embeddings from Google. I will tell a little bit about it in a while. We will use k-mean clustering. Then we have several clusters. After that, we can basically calculate transition matrix, transition probabilities among these clusters, get some finite state graph. The finite state graphs can be a connection to the other team. We have here at the workshop basically the ASR team. It was presented here already, and at the final step we are doing some annotation of the labels or the states. In our exercise it's very simple, but it is also one thing that we can look at during workshop to do it properly. This is basically what you can see as the output of the exercise. You will get some finite state graph like this, and you will see nodes, and you can get some textual transcription of the nodes. So for example here, I just took some examples. For example here for node 3, you can see that there are words that are close to each other, like slot, booking, opening, joining, unable, unavailable. So it means it is some part where the people want to get a table in the restaurant, and then for example here this cluster 9 where we found that there are many numbers, and after that we were looking what the numbers are, and these numbers are basically telephone numbers, because there is a telephone number shared during the conversation. Okay, so what is LAPSI? LAPSI is a model that can produce embeddings. It is from Google. I would say it is a very good model even for practical commercial tasks, because we use it for semantic search, even for our customer. So it was publicly released. It is a multilingual model, and it started with pre-trained BERT, and there is multilingual fine-tuning. The fine-tuning is done again with dual transformer architecture, and the fine-tuning is done on translation task. So you have text in source language, and you have text in target language, and then for the fine-tuning you can have pairs where the translation match, and where as negative examples you can take translations, other translations for the badge that you are using for computation. Here the loss function is additive matching softmax. Something similar was presented already during the diarization presentations. So the idea is similar the goal is to add some margin to the positive examples to make it even more separated and the task harder for learning. Now I would like to tell you a little bit about the other approach for dialog structure discovery, and the approach is using variational recurrent neural networks. So I would like to tell you why and what is it about. So you heard probably about autoencoders. So autoencoders, you can take for example, neural network to reduce the dimensionality of your input patterns to some lower dimension, and then the other network to do the reconstruction, or even the simplest case is probably PCA, principal component analysis, that can be used as autoencoder. But if you use neural networks, the networks are very powerful. So you can add as many layers as you like, nonlinearities. So the question is if the embedding space or the embedding vector is well represented. If you, for example, generate this randomly, if you get meaningful reconstruction, or if basically the things here is remembered like examples, if there is a generalization, and the answer to this actually is you can put some constraints to this vector, and this variational autoencoders can help you in these tasks. So here in this part are classical autoencoders, and in the bottom part there are variational autoencoders. So the difference is that the first neural network, the encoder, won't produce the embeddings directly, but it will create some distribution parameters. For example, if the distribution is Gaussian, it can produce mean and covariance matrix, and you can sample from this distribution, and then you can use the decoding, the decoder neural network to generate your example. Maybe how you can see it, we are training the neural networks, or the two neural networks together. So you can see it like here you have a part of the loss function that is related to reconstruction of the vector here, and you can see this part that is scale distance between the wanted distribution, this is here, and the distribution that you got. So you can see it like regularization in this latent space. Now, how it can be used for dialog structure Vojta was using variational recurrent neural networks. Just to remind you what are the recurrent networks. So you have network, and at each state you will output some hidden vector and send it to the input again. This is done at each temporal state, and here you can see the question that is encoded by the encoder neural network. You will get the prior distribution, and then it is used to generate the answer. The arrows are what depends on what. So for example, to generate the prior distribution, it is conditioned on the previous hidden states, and it is conditioned on the input to the neural network, basically the question. So you will get the prior distribution, you will do the sampling, and you will use the decoder to generate this answer. And there is the posterior distribution that is used basically to condition this prior distribution. So in the previous example with autoencoders, the distribution that was used for sampling was Gaussian distribution. But what is nice with this approach, you can use other distributions, and in this case, Vojta used discrete distribution and categorical. So you can simply say I have categorical distribution, and the number of categories or states is n. So you can train your model and use this states to describe your dialogue, and so it is trained using Gumbel softmax and so on. And if we have state labels, basically we can do the same as we did before. We can calculate transition probability, convert the transition matrix to graph, do some pruning, and annotate the labels. Okay. Okay, so this was this is all for this dialogue structure discovery, and of course when we are doing some work, we need also some ways how to evaluate if we are going to the right direction. So I will tell a little bit about how dialogue systems can be evaluated, and if it is wrong, or good or wrong approach. So we have corpus-based evaluation. For example, if we work with multivos, there is a board where you can compare with other systems. So some of the metrics is, for example, inform rate. It says if the entity that we were looking for was provided. There can be success rate, so it means if the entity was provided and information about it was shared correctly, there is joint goal accuracy. So joint goal accuracy, it's basically how to measure the state tracking. So it's the percentage of slots that were returned correctly for each state. So very often there is this is used for the state tracking task, and there is blue score for the scoring of response generation, basically what text you got from the dialog system. Of course, all these techniques or scores are artificial, because there are multiple possible right answers to questions often, and in the corpus you have just one or a little small subset. There is a huge discussion of what is the correct way, how to evaluate it, but we need to balance between the cost of the evaluation and also the speed of the evaluation, because we want to do the experiments quickly and so on. There are other possibilities for evaluation, simulator evaluations. So we can use a simulator of our user. Basically, this may be other dialog system, and there are metrics like success rate, if the goal was reached or not, in contact center, customer satisfaction rate, and so on. If you are looking for other objectives, for example, how the call was long, you can measure the dialog length, because it's directly related to the cost of the dialog system operation. And there is the most costly is, of course, human evaluation. So again, it can be task success, it can be duration. During workshop, Ondra Pátek would like to work on the evaluation approaches. So these were more corpus-oriented approaches, but you can have also some trainable measures. For example, the OpenAI, Google, they are already using approaches that are trained. Yeah, so I think I would conclude my talk with this, and now we have few minutes for questions, and after that we are looking forward to see you during the practical part. So thank you, and let's have some questions. So I'm sure that when you see the progress of these large language models, you have many questions in mind. How quickly these models will be deployed, when you will see it in office, when it will help you with your presentations, your reports, and so on. Okay.
Thanks for your presentation. Normally, how do we enrich a large language model with a target domain text?
Sorry, once more.
Is there a way to enrich the large language model with the domain-specific text?
Yeah, definitely. So it depends what large language models, what task you would like to use it, because there are these general language models trained for word prediction, but then you have large language models fine-tuned for particular tasks. And for example, this LoRa approach was a way how to use your data to enrich these large language models.
Petr, I had a question about evaluation. If you could just go back to some of the slides.
Okay.
So I understand the human, like, you actually have people and they try the dialogue system and they can either tell you whether they succeeded or you can count how many turns. This is reasonable, but of course it involves humans.
Yeah.
Let me skip the simulation, go to the first one. So this is something I'm asking out of ignorance, like, so I have some dialogue that I've actually witnessed between two humans, and then I'm trying to replace, let's say, the agent with a dialogue system. So I can feed it a utterance from the real user, and the system produces some response, and I can measure something about that response. I can measure its blue score compared to what the human agent had produced or something, right? But then what do I do? So suppose it's not what the human agent said. Do I still feed it the next user question or response, or what do I do? Because after all, the user might have said, I would like to fly to see my grandmother. And the real human agent may have said, which city are you leaving from? And then the dialogue system might say, who is your grandmother? Do I still respond with, I'm leaving from Baltimore?
So it depends on the evaluation. I think that in case of multivoice, it is really like this, even though it doesn't have sense. Some of the evaluations are really poor approximation of the reality, and we need to do something with it.
Okay, I mean, you can see what my concern is, that if the system had generated the correct response, then my next input does help the system track its state. But if the system was in some wrong state, even if I give it the real human user's input, the synthetic agent, my dialogue system, will go into some, basically it could go off the rails very quickly and just degenerate. So that was one. The other one was, how many dialogues do we need to get a reasonable sense of something? Like, are 10 enough? Do we need 100? Do we need 1,000?
So I think this evaluation came from the earlier research where the people wanted to have at least something, and it was hard to reach the dialogue goal. I think that the reasonable evaluation is really whether it reached the goal. The goal can be some shared information to user, basically user satisfaction, or a number of solved items and so on. And in commercial domain, I think it is easy to measure this. I think that researchers wanted some simplification. I think there is a huge discussion whether it is enough or these measures. I think these measures are not enough. It is we really need measures that are closer to the task that we are solving, and I think that this is because also the reason why Ondra is wanted to investigate this. And yeah, please comment.
So actually, I want to comment on the first question because I think it's really important. The question was if you have a dialog history, dialog prefix, and the system generates a response, then the original and the dialog agent, the real one, actually generate other response than the system provided. In the next turn, we are not evaluating with the same dialog history. So the thing is, what we will use in the lab, we will always assume that the ground truth dialog history. So the evaluation is very skewed in the sense that for some dialog histories, the system will not be trained, and you will give him the dialog history which is considered ground truth from its point of view, and you will then evaluate just the next response, not the whole dialogue.
Okay.
So this is very biased, obviously.
Is it biased in favor of the system, meaning the system might make a mistake, but because you give it the correct history at the next turn, you're putting it back in the right
exactly.
state? Okay.
It is very, very biased in the sense, and and obviously you need annotations for that, or so it's biased and expensive. So yeah, so this is the main thing which I want to stress, because you will get hands-on with this evaluation, and it will be over-optimistic.
Maybe, and can you give some ideas about the number of examples? If
Another thing, we will be using large language models, and it seems that you need very few number of examples. But I actually assume they saw the whole training data set, so they are cheating. So I cannot comment on the number of examples because it's very hard to evaluate anything with large language models if you don't know what the training data is.
So okay, do we have more questions?